Chapter 21, Electric Field. Electric field covers the electric field lines, the electric field due to a point charge, the electric field due to an electric dipole, the electric field due to a line of charge, the electric field due to a charged disk, a dipole in an electric field. You can find them in a timeline. Electric field lines. Charges and forces are closer look. Since the charges do not touch, how does the first charge Q1 know of the presence of the second charge Q2? This question about action at a distance can be answered by saying that Q1 sets up an electric field in the space surrounding it. Another action at a distance problem arises. If we move Q1, say, towards Q2, does the electric field at Q2 and thus the force acting on Q2 change immediately? The answer is no. Instead, the information about the movement of Q1 travels outward in all directions as an electromagnetic wave at the speed of light, c. The electric field, temperature field, and pressure field are all scalar fields because temperature and pressure are scalar quantities. The electric field is a vector field. It consists of a distribution of vectors, both with direction and magnitude. The electric field E at point P, due to the charged object, is defined as E is F over Q0. Now, you put a test charge Q0 at point P, it suffers a force F. F over Q0 is defined as the E at this point. Thus, the magnitude of the electric field E at point P is E equals F over Q0. And the direction of E is that of the force F that acts on the positive test charge. This is a positive test charge. What the test means? It means it charge is very tiny, very small. It will not affect the original electric field. So with F over Q0 get E. Q is positive charge. In this case, E and F are the same direction. This is the E. The metric system unit for the electric field is, this is a Newton, this is a Coulomb. It's a Newton per Coulomb. To examine the role of an electric field in the interaction between charged objects, we have two tasks. One, calculating the electric field produced by a given distribution of charge. And two, calculating the force that a given field exerts on the charge placed in it.
We'll use this apparatus to show the electric field configuration around various charged objects. Particles suspended in the fluid inside this chamber will line up in the presence of an external electric field. The alignment shows the lines of the electric field. If we put this small metal cylinder on top of the chamber and charge it using this pistol, this is the shape of the electric field from the metal cylinder. Here is the electric field between a pair of parallel metal plates, one of which is positive and the other negative. Here is the field between two oppositely charged circular conductors. Notice the absence of an electric field inside the inner conductor.
Some electric fields, say this is a very small one, this is inside the copper wire of household circuits, 10 to power -2. And the biggest is at the surface of uranium nuclei is 3 times 10 to the power of 24. Electric field lines. Electric field lines provides a nice way to visualize patterns in electric field, although they are not real. The relation between the field lines and electric field vectors, it is because electric field is a vector, so you need represent the direction and magnitude. 1. At any point, the direction of the straight field line or the direction of tangent to a curved field line gives the direction of E at that point. And 2. The field lines are drawn so that the numbers of lines per unit area measured in a plane that is perpendicular to the line is proportional to the magnitude of E. This second relationship means that where the field lines are close together, E is larger, and where they are far apart, E is small. Look at this negative charge. This is a positive test charge. We put it here, the attract. So this is the direction of F. And we see this is the electric field line. F is toward the negative. Okay. Electric field lines extend away from the positive charge where they originated and towards the negative charge where they terminate. This is electric field produced by charges. Okay. Now, if we have an infinite uniform carried charge distribution plate, by symmetry reason, the field of electric field must be perpendicular to the plane. Okay, everywhere perpendicular to the plane because of symmetry. So we can write it in this way: they are uniform and perpendicular to the plane. This is the two same size positive charge. This is their electric field line. This is the electric dipole. One is positive, one is negative. Okay, with the same magnitude, a different sign. This is the electric dipole. Sample. How does the magnitude of the electric field vary with distance from the center of the uniformly charged sphere in the figure? This is a uniformly charged sphere. We want to find the magnitude of electric field. And we know electric field terminate at negative charge. So it should be like this one. Okay. And we see if we make this distance, they get sphere shear. Okay, sphere shear. And the area of the sphere shear is 4 pi r squared. And the number per unit area is total number divided by 8. This is proportional to E. So we know that E is approximately proportional to R, 1 over R squared. The electric field due to a point charge. To find the electric field due to a point charge Q, or charged particle, we put a positive test charge Q0 at any point at distance r from the point charge. Okay, and with positive, they always repel with each other. So this is the direction of the electric field. Okay, and by definition, E is F over Q0. And according to the Coulomb's law, F equal to 1 over 4 pi epsilon 0 Q0 over R squared, R hat. And the Q0 would cancel out with this Q0. So E is equal to this one by a single charge. Okay. R hat is a unit vector along the radius from charge. This can be have a charge. This charge is the one which produces electric field. Okay, not the one inside the electric field. Okay, so r hat is a unit vector along the radius from charge q to the point in concern, and this is to the point in concern. Q is positive, so E along the I hat points outwards. If Q is negative, so E is negative, R hat is points inward. We can find the net or resultant electric field due to more than one point charge with the aid of the principle of superposition. We know the force acting on the object by many charges equal to F, the force 0, 1 by charge 1 acting on 0, or plus the force on 0 by charge 2, or the force acting on 0 by charge 3, and so on. And E is F0 over Q. We put this F0 inside. We get F01 Q0, FO2 over Q0, FOC over Q0, and so on. And this is the electric field produced by Q1 at this point. This is E2, this is E3, equivalent sigma EI. This is called the principle of superposition. Sample. Figure shows 3 particles with charges Q1 plus 2Q, Q2 minus 2Q, and Q3 minus 4Q. Each a distance d from the origin. They are the same, d. What next electric field E is produced at the origin? We find the E at this point. And we look at this. This is a Q, this is a Q, so this is 2Q, this is minus 2Q. So at this point, this E produced is equal this direction. And this negative number is equal this direction, okay? This negative number goes this direction. So we get E1, E2, E3, okay? Because they have the same D, this is the same charge, so these two E are the same. And this E is double this one. So we put this one together, we get this situation. And we found we put these together, this E is along the direction X. And the E component along Y cancel out. Okay? So the E equal to 2E3X equal to E3 over cosine 30 degree. And we put a number inside. E3 equal to 1 over 4 pi epsilon 0. This is a 4Q. 4Q d squared. And cosine 30 degree is 0.0688, and we get E. The electric field due to an electric dipole. This is the electric dipole. A couple charges with the same magnitude but opposite signs of charge. So in this case, this is positive charge Q, this is negative Q. And the distance between them, the D, very tiny one. And we define a dipole, P. This P equal to D, QD. The D is from negative point positive, okay? And we will prove the electric field on this line, far away from it, E equal to 1 over half pi epsilon 0 P over Z cubic. Now, we know for a point charge, this is a 4. Then we can know, because electric dipole have 2, so cancel 2. And here, for point charge, Z squared. Now you have Z cubic. Why? Because P including a D. And we cancel our distance around this one. This is the one I'm going to prove to you. Okay? Now, the electric field at this point, which is distance Z to the center of the dipole, which is pretty larger compared to the D. And then let's say, so the RD, R positive, this is positive, to this point, R positive, equal to Z minus half D. This is half D. Z this is the center, okay, half d. Z is much larger than d in our case, okay? So we can take it z squared out. It's 1 minus d over 2z squared. And when you find the electric field at this point, by this point d, we need to use 1 over r squared. So with 1 over r positive square equal to z minus 2, 1 minus d 2z minus 2. And this one, we know z is much larger than d, so this is very small compared to 1. Now we have a formula in calculus, 1 plus x power to the n. When x is much smaller than 1, we can write it approximately equal to 1 plus nx plus n plus n plus 1 x squared over 2 factorial, and so on. So in this case, we put this inside. This is equal to z minus 2, 1 minus 2 minus positive 2, cancel the 2, d over z, and so on. For the same reason, we can find r minus to this point. R minus equal to z plus half d. Z plus half d. We take z is much larger than d, we take z out. Okay. And we also reverse it. You get z minus 2, 1 plus d plus minus 2. And we also, this is much smaller than 1, we use this one equal to nx, so equal to z minus 2, 1 minus 2 cancel d over z, and so on. Then we put together this E at this point is E produced by positive charge plus E produced by negative charge. That's 2. And we put the number inside. This is a Q over 4 pi to 0 E. You have 1 over R positive square. This is 1 over R negative square. And we put the red one as we get previous page, z minus 2, 1 plus dc. And this one is z minus 2, 1 plus d over c. Now we find out that this term cancel out. And this term double. So finally we get q over 4 pi 2d over z plus z squared. Okay, z squared equal to this one. And we combine this qd with p. Here we get it canceled out with this answer we know. This is the electric field produced at the line, connected these two lines, far away from the dipole. Electric field due to a line of charge. We now consider charge distributions that consist of a great many closely spaced point charges that are spread along a line, over a surface, or within a volume. Such distributions are said to be continuous rather than discrete. Since these distributions can enclose an enormous number of point charges, we find the electric field that they produce by means of calculus, rather than by considering the point charges one by one. Electric field due to a line of charges. Now, here we have a uniformly distributed line, okay, which is a ring, it's a ring with radius r. We are asked to find an electric field at point P, which is on its central axis, distance z from the center of the ring. The radius of this ring is capital R. Okay. How do we find the electric field at point P on the central point? We divide this ring into a very small section, we call it ds. ds carry charge dq. The E at P looks like a 2 point, is the electric field produced by point charge, ds, is along this line. The ds equal to 1 over 4 pi epsilon dq over r squared. And this r squared equal to, in this rectangular, equal to z squared plus big R squared. And the dq equal to ds multiplied by the charge density, rho. Okay. The rho equal to whole charge q divided by its length, 2 pi r. Okay. Now, because of the symmetry situation, we take another section ds, same length in the another end of the diameter. Okay. And this charge will produce E at point P like this one. The magnitude dE must equal to this dE because of the symmetry reason. And we can find out, okay, these two, combine these two, only the Z component, the E component along the Z direction overlapped. The perpendicular to the Z direction, they cancel out. So we take the charges in pair, many pair. Each pair, their dE is along the Z direction. So finally we say each dE, its component along the Z direction makes final contribution. Okay? So we have the dEz, they make contribution, equal to dE cosine theta. And the cosine theta in this direction is equal to z over r. And r is equal to z squared plus big R squared. Okay, then finally we do it. The E equal to dz integration. Okay, dz equal to dE cosine theta. This is dE, this is cosine theta. Okay, we put it. dE equal to 1 over 4 pi epsilon 0 q lambda ds r squared. This is z. Cosine theta equal to, first z over r. Z over r equal to z squared over big R squared. Okay? And we do the integration wrong. Okay? Let me write it. This is z lambda. Okay? This is a square. This is 1. So there was 3 over 2, 3/4, 3/2. Okay? So we do the integration. It looks very complicated. Actually, it is not, because what we do the integration is along this one, the ds. And all these z are nothing to do with s. So we can rewrite this integration as, put this one inside, integration ds. And this integration diffraction equal to total length of this ring, 2 pi r. 2 pi r is the length multiplies density, you get the q. So the E equal to zq over 4 pi z squared r. Okay, we get the answer. Now, if the r is approach to 0, so this ring become the point charge. So this become the electric field, the point charge, like Coulomb's law. So with r equal to 0, z squared, we get this cancel 1z, we get q for pi z squared. This is the electric field produced by point charge, right? Sample. Figure shows a plastic rod having a uniform distributed charge minus q. Totally is minus q. The rod has been bent in a 120-degree circular arc of radius r, small r. We place coordinates axis such that the axis of symmetry, this is the axis, of the rod line along the x-axis. So this is the x-axis. Okay. The orange is at the center of a curvature, P. Okay. In terms of Q and R, what is the electric field E due to the rod at point P? Now, we have a symmetry with respect to axis. So, if we take a very small section of charge here, ds, corresponds to d theta, then we can have another one by symmetry, okay? In this case, because the negative charge is towards the asymmetry, so we find only component along x direction makes final contribution. The E along y direction will cancel out with each other. We take pair, they always cancel out. So what conclusion is, the final E is along the x direction, right? Yeah. Okay, then we find the dE produced by this one, at this point, dq over 4 pi epsilon r squared. What is dq? dq is ds related, equal to lambda ds 4 pi r squared. Okay, what is lambda? Lambda equal to q, ds equal to r d theta. And so along x is dex equal to de cosine theta. Okay, and de is lambda ds 4 pi over 4 pi epsilon r squared cosine theta. Okay, and then we ds, what is ds? ds is r d theta. The r cancel out 1, we get the r d theta. Okay, and then we do the integration. This integration is very simple because cosine theta is sine theta. The r is constant, okay? And we're starting from minus 60 degree pi over 3 to positive pi over 3, okay? And this is a very simple integration. I'm going to do it, not do it. So we get equal to lambda over 4 pi epsilon 0 rho sine theta from minus pi over 3 to positive pi over 3. We get this number. And the lambda is q over the length. Q over what the length is about, this is 120, so it's about 1/3 of circumstances, okay? 2 pi r over 3, okay? We put the lambda inside this one, and we get E, it's by symmetry, only EX, okay? And we put this one lambda inside, we get this answer. This is a simple calculus. We can calculate, use the electric field P by uniform distributed charge. So the calculus. In this book, because of the charge, we use the Q, symbol Q. The unit is coulomb. Linear charge density is Q over meter, lambda we use. Surface charge density, sigma, is coulomb over square meter. Volume charge density, rho, coulomb over meter cubic. A thin non-conducting rod of finite length carries a total charge Q, spreading uniformly along it. Show that E at point P on the perpendicular bisector, this is a bisect, half bisect, in the figure is given by E equals Q over 2 pi epsilon 0 y. Y is the distance of P to the rod. This is a constant in this question. Okay. Let me see. We pick up very small, tiny dq. This is a dx. Location at x. The center of this rod we take as the origin of the axis. Okay. And then for this part of dx, very small section, we charge dq. The electric potential at P is equal to 1 over 4 pi epsilon 0 dq over r squared. This r is the distance P to this point in this question is equal to x squared plus y squared square root. Okay? And the dq is equal to lambda ds dx. Lambda is the charge density, linear charge density, okay, which is equal to Q over L. Okay. All right, so this is dE. And we will see that if we symmetrically we take another dx this relatively to this one. So you have dE along this direction. We can tell that the combination of these two dE must be along the y direction. Right? By symmetry reason. So dEy is the final result. The final result. And the dEy equal to dE multiplied by cosine theta. And the cosine theta in this triangle is equal to y over square root x squared plus y squared. Okay. So cosine is y over x squared plus y squared. Okay, then we know so dE, the total E must be integration of dEy equal to dE cosine theta. And dE is this one. Cosine is this one. We put them. So dE equal to 1 over 4 pi epsilon 0 lambda dx over x squared plus y squared. And cosine theta equal to y over square root x squared plus 3. And then we combine these two, we get it. Answer is y lambda 4 pi epsilon 0 x squared plus y squared to the power of 3 half dx. Okay. Okay. And I see this integration is not easier to do it. We check the integration table, okay? And integration x is minus half L to positive half L. And we check the integration table, we find dx over x squared plus a squared to the power of 3 half is equal to x over a squared plus square root x squared plus a squared. So compared to this one, a is equal to y. So we put this one inside, we get it. The answer is this. The integration is from minus half L to half L. And we put the number inside, we get the E. Okay. This is the one we want to approach. The electric field due to a charged disk. The electric field due to a charged disk. We are looking for the electric field at point P, which is on the central line by the charged disk. We can look at the disk is composed of many rings with the center overlap to that of a charged disk, and their radius varies from 0 up big up to capital R. We know from previous calculation the electric field at point P on the central line, which is the distance z from the center of the ring, is E equal to zq 4 pi epsilon 0 z squared plus r squared to power of 3 half, where q is the charge of this ring. Now, in our question, this E is part of our E because we have to find the E produced by many different rings. So we label it dE. The charge on this ring is dQ. Now let's see, what is the dQ? dQ on this ring is equal to surface charge density rho times its area, surface area. Now, and its surface area equal to the circumference of the ring, 2 pi r, multiplied by its width dr. This is area. So this is sigma dA is the dQ. We put them up, we get this answer. Okay, put a sigma z 2 pi r dr, this one. This dE is produced by this ring with radius r. And we have a many. And we know that by symmetry, all the E along the axis. So the total E, of this electric field produced by different ring is sigma dE, or integration of E. Because they are in the same direction, you just put them together. Okay. You do the integration of this one. This integration is not hard, it's easy. You see, 2r dr is equal to dr squared. You have r squared. And the radius is from r, it's very small, 0, big, up to capital R. This is a range of r. Okay. And when we do this integration, we rewrite 2r dr as dz squared over r squared. Well, how? Because 2r dr is dr squared. Okay, you do the dr squared, you get 2r dr. And the z is a constant. We put it d constant is 0. Why? Because in the denominator we have z squared plus r squared. So in write this one, okay, we can see this is like, suppose z squared plus r squared is x. This is a dx over x to power 3/2. Okay, and the integration is from r equal to 0 to capital R. It's very easy. We can get this answer. Okay. Okay. Now let's look at the extreme situation. Suppose the R approach the infinity. That means this disk becomes an infinite plane with a uniform charge density sigma. In this case, R approaches infinity, so this term becomes 0. So the E becomes sigma over 2 equal to 0. Or Z equal to 0. That means the point P is on the surface. Okay? And Z is 0, this term is equal to 0. So E equal to sigma over 2 epsilon 0. Okay? What does this mean? Physically, this means the electric field on the surface of the infinity plane charge is sigma over 2 epsilon 0. Okay, we will have this conclusion in the next chapter. A point charge in an electric field, that's very simple. It will be exert a force F equal to QE. The electrostatic force F acting on a charged particle located in an external electric field E points E in the direction of E if the charge Q of the particle is positive, and in the opposite direction of E if Q is negative charge. Measuring the elementary charge, American physicist Millikan measured the elementary charge. So it's oil drop experiments, very famous experiment in physics. Okay, now this you spray oil, so many small drops of oil with some charge, and this is an electric field inside. Okay, when the oil drops go inside, because of a charge, it can move up the bar because of this is electric field. And then you use the microscope to watch it. And what we found is the charge on any object should be integral number of elementary charge. The n can only be integral number, cannot be point something. Okay, and this elementary charge is 1.60 times 10 to the power of minus 19 coulomb. This is the charge which electron or proton carries. Because of this experiment, in 1923, he got Nobel Prize in physics. This is American. This is a Millikan oil drop.
This Millikan oil drop apparatus is similar to the device used in the first successful measurement of the charge on a single electron. Inside this chamber are two horizontal metal plates separated by about 2 centimeters. We'll spray a fine mist of oil droplets between the plates and observe them as they fall. If we apply a high voltage to the plates, some of the oil droplets are accelerated upward or downward because of the presence of minute electrical charges on the drops. We can reverse the direction of the field with this switch. Let's follow the motion of one of the drops as the field is reversed. First, the field is vertically upward, then off, then vertically downward. Notice how the droplet has reversed direction. Off, upward, off, downward.
Inkjet printing. Let's look at the inkjet printing. Okay, this is inject the ink. Okay, this is an input signal based on the information you get, and it go to electric field, and hit the paper and print it out. And this ink drop is about diameter 30 micrometer, about half the thick diameter of your hair. Okay, the velocity is 18 meters per second. In each second, you have 100,000 drops past this room. Okay, and then we see after the ink get into the electric field, it deviated. Figure shows the deflection place of an inkjet printer, okay, with superimposed coordinates axis x, y. Okay, an ink dropped with a mass m of 1.3 10 to the power of negative 10 kilogram, and a negative charge of magnitude q equals 1.5 times 10 to the power of negative 13 coulomb enters the region between the plates, initially moving along the x-axis with speed vx 18 meters per second. The length L of the plate is 1.6 centimeter. The plates are charged and thus produce an electric field at all points between them, uniform E. Assume that the field E is downward, uniform, and has magnitude of 1.4 times 10 to the power of 6 Newton per coulomb. What is the vertical deflection of the drops at the far edge of the plate? This one. Okay. The gravitational force on the drop is small relative to the electrostatic force acting on the drop and can be neglected. Now look at this one. Well, we want to find the deviation. Why? Since there is no acceleration, so the y you could have at squared, because this is a uniform electric field, uniform force, uniform acceleration. So this is constant acceleration along y direction. This A is equal to F of m. F is electric F, the QE over m. The T is the time from here to here. Okay, the velocity is v 18 meters per second. Length is L, so the T equal to length L over Vxl. We put this one inside, we get a Y. We get a Y. This is A, this is a T, and we put everything inside. Okay, so we get a Q is given 1.6 times 10 to the power negative 13. Okay. E is 1.4 times 10 to the power of 6. L 1.6 times 10 to the power of negative 2 squared over 2. M is 1.3 times 10 to the power of negative 10. And V is 18 squared. We get 0.64 is very small number. Okay, so we'll be very careful. Control the charge Q within a few percent is essential. A dipole in an electric field. A dipole in an electric field. This is a dipole, minus Q, positive Q. A distance is D, which define P, the dipole, P equal to QD. Q is the charge each one carries. D is the distance from negative to positive. Okay, it's a vector. Okay, and we have uniform electric field E. Okay, electric field E. So the positive charge will be exert a force F to the right, and the negative charge will be exert force to the left. And we see we have a torque around the center of mass. This is a F. The distance perpendicular distance is half D sine theta. And this one is F half D sine theta. Two half become pushed. We have a minus sign here. The reason is we take this is a theta counterclockwise, a positive. And this torque is go this way, clockwise. So it is negative signs. Okay, negative sign. And F equal to EQ. And we combine Q and D, this is a P. So minus QD E sine theta. All right? And we write it in a vector stream. We say this is tau equal to P cross E. Remember, tau equal to P. Torque on the dipole. Okay. So on dipole in the electric field, it suffer a torque, which equal to P cross E. Look at this one. This is a P. This is E. So with P cross E, go inside. Go inside. Okay. This is a clockwise. Okay. Potential energy U of an electric dipole. Let's see, we set U 90 degree equal to 0. Now, theta equal to negative, this is a positive here, negative here. In this situation, we set the potential is equal to 0. And then delta U equal to U theta minus U, potential 0, is a U theta. By definition, it should be minus W. Okay? Minus W, the work done by the electric field. Okay, and W equal to tau d theta, integration. Okay, integration, and then you do is from 0, 90 degree to theta. Okay, what is tau? Tau equal to P cross E. This is a minus PE sine theta because direction is the negative direction of theta. Okay. This is a definition from here, and we do the integration. Minus, minus, we get a positive. And it's starting from 0, 90 degree to theta. And we do the integration, we get a cosine. This is a minus, minus, positive. Sine theta, this is integration is minus cosine theta. Okay, that's the answer. And we rewrite it as U theta equal to minus P dot E. Okay, so electric dipole in the electric field, it will suffer the tau equal to P cross E, and it will have a potential energy minus P dot E. Example, a neutral water molecule H2O in its vapor state has an electric dipole moment of magnitude 6.2 times 10 to power of minus 30 coulomb.me. How far apart are the molecular centers of positive and a negative charge? Okay, this is dipole. You have a charge. Okay, charge, how much charge? You see, oxygen you have 8. Hydrogen we each have 1. So altogether is 10. 10 electrons, 10 protons. See? So D equal to P over 10E. This is a total charge. This is P is given. Okay, so we'll find the D. We'll put it then inside, we get a D. D is 3.9 10 to the power of negative 12. That's 3.9 picometer. Now, which is about 4% HP bond distance. This figure is exaggerated, okay? If the molecule is placed in an electric field of 1.5 times 10 to the power of 4 Newton per coulomb, what maximum torque can the field exert on it? That's very simple because we know the E, we know the torque, so E equal to, E, we know P, so the EP maximum is E can P, okay? C, how much work must an external agent do to turn its molecular end to end in its field, starting from its full alignment position, for which theta equal to 0. Now, so we want to turn it equal to minus, okay, the work equal to the outside work done is minus initial. Okay, so we'll put this one inside. This is close to 180. This is minus 1. This is positive. This is a positive. But we'll get this one. Okay. 2 PE. About 1.9 times 10 to the minus 5 joule. And we compare to 3 kT over 2, which is 6.2, 10 to the power of negative 21. This is larger than this one, about 4 order of magnitude. What are this? Remember that this is the average energy at a temperature of the molecular at temperature T. So this is a routine temperature. That means at the room temperature, the dipole thermal energy is much larger than the one needed to turn it around. So it's very easy to disturb. So easy to be disturbed. As a result, the molecules bound together in groups of 2 or 3 because the negative oxygen end of one dipole and the positive hydrogen end of another dipole attract each other. Next chapter, chapter 22, Gauss' law. Welcome you make a comment and give suggestions so that this program can be more helpful. Acknowledgement. This video clip is a part of my lectures on college physics during 1990 to 2021, based on the adapted textbook, Principles of Physics by Holliday, Resnick, and Walker, published by Wiley. The demo videos were bought from a company in USA by my university for teaching. They help a lot. I'm sorry for not remembering its name to show my appreciation. It seems that they came from the University of California, Santa Barbara, where I got my PhD in physics. Thanks God.